So, all right, next up, we have the M-26 realignment over the Firesteel River. Ethan, I believe you're sharing our slide.
Yep, can you hear me?
I can hear you.
All right, we ready to go?
We are ready.
Good morning, everyone. My name is Ethan Carpenter, and I am joined by Kyle Provo to present to you the realignment of M-26 over the Firesteel River. In the following order, the project's background, the scope and constraints that are associated with the overall design of the project, the proposed bridge location, horizontal and vertical alignments, the corridor modeling, pavement design, open ditch design, the guardrail calculations, maintenance of traffic plan, permanent signing and pavement marking details, and finally the recommendations made to MDOT and Fishbeck. M-26 is located in Michigan Peninsula, connecting the cities of Rockland to Houghton and continuing to Copper Harbor. Located in Ontonagon County, a bridge along M-26 over the east branch of the Firesteel River has failed its annual structural inspection and must be replaced. For the overall scope of the project, the team was tasked with designing a user-friendly roadway to AASHTO and MDOT specifications and determining a new bridge location with additional design for the proposed vertical and horizontal alignments. Three major constraints were applied to the project. First was the development of a maintenance of traffic plan that would maintain two-way traffic throughout the entirety of the construction process. Second is limiting the amount of wetland that will be impacted by the new construction. Third is to keep all proposed design within the right-of-way. The first major design decision was the proposed location for the bridge. We posed three design options and systematically eliminated each design until only one viable choice was present. One option was immediately eliminated, and that was to construct the proposed bridge in the exact position the existing bridge currently stands. This was done because there's no option for a detour route around the current construction limits, so we must locate the new bridge to either the north or the south of the existing bridge to properly maintain traffic. This left the team to analyze the constraints of building the bridge to the north and the south. The north bridge location was in direct conflict with a large area of wetland, which was one constraint posed by MDOT for the project. The second option for eliminating the north bridge design was the super elevation runout location, which will be further discussed in the next design section. The final decision was to go with the southern bridge design. When implementing the horizontal alignment, the team needed to review how the super elevation would affect the cross slope of the shoulder. It was determined because of the climate of the Upper Peninsula, it would be best to eliminate the amount of possible water melt that would run across the travel lanes. So it was decided to use a max of 5% for the rate of super elevation. This would allow the high side shoulder within the super elevation to peak at a 1% grade away from the edge of pavement. Next was determining the radius to use for each curve. This was done by using MDOT's R107-H specification for super elevation and pavement crowns. With a 50 mph design speed and a max super of 5%, it was determined by interpolation that our minimum radius for both curves would be 1,850 feet. Finally, for the horizontal curve, we needed to analyze where the super elevation transition would end. This transition extends 2/3 outside of the curve. To determine this location, we use microstation smart lines by tying the 2/3 length to the endpoints of the curve and adjusted the radius until the transition no longer continued onto the bridge deck. As you can see in the diagram, the north bridge does not allow a super elevation runout of the proposed length. The only option for the northern proposed bridge alternative is to use a straight line method of design, which is considered to be a less viable option. This led us to ultimately choose the southern proposed bridge location with a radius of 1,900 feet to allow for a 50-foot transition zone at the bridge. The final curve data is seen with curve 1 and 2 having a super elevation of 5% and 2.7% respectively. The phase of design was to develop a vertical curve that met MDOT standards and followed the existing terrain without creating any additional costs associated to earthwork. The first design was to maintain a maximum slope of 5% vertically. The second was to not allow a low point on the bridge and to maintain a 0.3% slope across the entirety of the bridge. Before beginning the process, we needed to finalize the rate of vertical curvature for our sag vertical curves. Using AASHTO Exhibit 375, we determined with a design speed of 50 miles per hour that the design value to be used is 96. This allowed the team to finalize the vertical curve design and maintain a proper bridge elevation, as well as keep the low point of the roadway off the bridge deck. The corridor was developed within MicroStation using template drops created in Bentley's GeoPack application. GeoPack allows for users to model the proposed roadway through the creation of cross-sectional templates, which you can view in this current slide. This three-dimensional modeler then creates the roadway by using a template to display the lines which will make up the proposed corridor. This process first begins by creating the template and tying the points within it to specified restrictions based on the adjacent points, including maintain select grade percentages, depths, and distances. This allowed the template, when modeling, to hold its form, especially when displaying the super elevation sections within the curves. Next was managing the end conditions, which can be viewed in the template as the lines and points that make up the ditches and shoulders of the roadway. We allow the points at the end of these lines to solve the existing topographical elevations within the design file, which ultimately creates the ditches and solves for the optimal condition to the roadway surface. We allowed our template to solve for 3 separate conditions with the following priority within the corridor. First was a bottom trapezoidal open ditch. Second, a flat roadside condition. And lastly, it was a 1-on-4 slope, which would extend infinitely until it intersected with the existing ground elevation. With the template completed, we can then create the 3-dimensional design file of our corridor. Revisions are done until our corridor is constructed to the most optimal design, then used within all the design processes going forward. I would now like to pass it off to Kyle for pavement design.
Our team designed both flexible and rigid pavements. Our first step was to analyze the data we received from MDOT. With an average annual daily traffic of 1,425 vehicles per day, design life of 20 years, and 99% reliability, we're able to determine the other factors necessary for design. In the pavement design, the structural number for flexible design and concrete slab depth for rigid design must be assumed. Through trial and error, the actual values will be determined. Assuming a structural number of 3 for flexible and 7 inches for rigid, we can now calculate the estimated single axial load acting upon the pavements. Using the Easel equation, we find the corresponding HMA easel to be 843,500 and the concrete easel is 180,700. It's time to check to see if our assumptions are correct. Using the basic design equations and solving for the structural number and slab depth, we determined that our assumptions were adequate. If the calculated value differed from the assumed value, the axial load equivalency factor, FEI, would change, and the easel value must be recalculated and plugged into the associated basic design equations until the same values were obtained. With an adequate structural number and slab depth, we can now solve for our minimum typical cross-section depths. Using the table of recommended minimum thicknesses supplied by AASHTO and the depth equation, we determined a minimum HMA depth of 3 inches, an aggregate base of 6 inches, and a total subbase of 13 inches. Section for the concrete was determined as a slab depth of 7 inches, an ag base of 6 inches, and a subbase of 12 inches. This is the point where we analyze our pavement alternatives. We selected 5 different criteria and weighed them to what MDOT would hold most important. With cost and life at the highest priority and aesthetics at the lowest priority, we continued with a flexible HMA pavement design throughout the rest of the project. Now with our minimum cross-section depths determined, we reviewed MDOT's HMA selection guidelines, and because we are in Michigan's Superior region, we use the following mixture types: 5E3 as the top course, 4E3 as the leveling course, and 3E3 as the base course. These mixture types have minimum application rates of 165, 220, and 330 pounds per square yard respectively. HMA has an assumed application rate of 110 pounds per square yard for a 1-inch thickness. Therefore, these minimum application rates will not represent our HMA depth because when combined, they are well beyond our minimum calculated value of 3 inches. Our HMA depth is now 1.5 inches for the top course, 2 inches for the leveling course, and 3 inches for the base course. After re-examination, we have determined that our proposed typical section be an HMA depth of 6.5 inches, an ag base of 6 inches, and a subbase of 18 inches. This is our proposed typical normal section with a 2% crown. Our team designed a typical MDOT trapezoidal ditch with a 6-foot bottom and 1-on-4 side slopes. As seen in the vertical curve section, there is a 5% slope running down to the river. MDOT recommends that the max fill height of our ditch is at least 1.5 feet below the shoulder, so we use the fill height of 2.5 feet to determine our max velocity and flow. Utilizing these equations, we determined a max velocity of 17.44 feet per second and peak discharge rate of 697 cubic feet per second. After calculating our max flow rate, we determined the amount of runoff After determining our max flow rate, we determined the amount of runoff that our ditches will receive. With a drainage area of 2 acres, rainfall intensity of 4.79 inches per hour, and runoff coefficient of 0.9, we determined a peak runoff rate of 8.622 cubic feet per second, therefore determining that our ditches can definitely sustain our runoff. When designing guardrail, the team used a geometric approach using MicroStation with the help of MDOT's worksheets. To avoid a large amount of guardrail throughout the project, the team designed all fill slopes at a 1-on-4 grade, which is the maximum value before guardrail is required. This meant that the design was only needed at the bridge approaches. We first determined our clear zone distance LC and runout length LR from MDOT's road design manual. These values are based upon design speed and ADT. Using these values, we geometrically created triangles and determined our runout line. This runout line is important because it determines where the third post of the approach terminal must be placed. Even though the length of need for 2 of the designs are totaled at 65 feet, both the bridge anchors and approach terminals have set constructed lengths, and there must be a minimum L1 value of 25 feet. Therefore, the runout line will not run through the third post. This is an over-design and will only maintain a safer approach to the bridge and the river. Type MGS8 guardrail is used because it is MDOT's current standard for all freeways. All approach terminals have a 1-on-15 flare and will utilize the MSKT head at the end of each terminal. Maintenance of traffic was a key component in the design of M-26 due to the lack of detours. There are no alternative routes for users to bypass construction, and this is why our design was essential for maintaining traffic. For this project, 3 stages of MOT were necessary. Stage 1 is used for most of the construction and consists of temporary concrete barrier along the south side of the road and through both sides of the bridge. This is to limit vehicular access into the construction zone. Just east of the bridge, the temporary barrier ends, and barrels are then used to guide traffic to the project's limits. Stage 2 is broken up into 2 sections. Stage 2A is necessary for connecting the new eastbound lane to existing. Temporary signals are placed at each end of the connections, and all traffic will be directed onto the existing westbound lane. Thus, the signals will help direct one-way traffic and avoid collisions. Barrels and temporary pavement markings will guide users through the work zone. Stage 2B is similar to 2A, in which the temporary signals will remain in place, and now all traffic will be directed onto the new eastbound lane. The new westbound lane will be closed in order to connect to the existing roadway, and one-way traffic on the eastbound lane will be guided by the temporary signals. Once again, barrels and temporary pavement markings will direct users through the work zone. Stage 3 is the final stage of MOT and is needed for the removal of the existing bridge and pavement. Two-way traffic will be maintained on the new roadway, but will be offset 6 feet to ensure work zone safety while removal is completed. Temporary pavement markings and barrels along the north end of the new roadway will provide direction through the work zone. Ethan will now continue with permanent signing and pavement markings.
Permanent signing and pavement markings first began by determining if there were any available passing zones within the project. Through graphical means and the available site distance, the team found that there were no passing zones within the project. With this information, the team started design at the bridge where most signs would be located and worked out from there. All informational and object marking signs are placed at the bridge approaches, and regulation and directional signs are placed according to their specified wording. Warning signs were determined through MDOT design placement application guidelines to be placed at a distance of 360 feet from the bridge approaches for a posted speed of 45 miles per hour. If any warning sign is located within a curve at the 360-foot specified distance, they are to be moved before entering the curves to allow drivers to prepare for the approach. All pavement markings were designed according to specified passing lanes. Since there are no passing zones to the west of the bridge, the length of the center line between lanes were painted a 4-inch yellow double solid marking. East of the bridge, however, required a 4-inch yellow solid broken and a 4-inch white broken pavement markings to indicate the truck passing zone when climbing the hill. All pavement markings will be done with a waterborne paint within recessing of the pavement surface. Before markings can be applied to the bridge, all curing compound will be ground off to allow for proper bondage to the concrete. For final recommendations, the proposed bridge will be constructed to the south of the existing superstructure, and horizontal and vertical alignments will match accordingly. Both flexible and rigid pavements were designed, and through an analysis of alternatives, we continued our design using a flexible HMA pavement. We designed typical MDOT trapezoidal ditches with a 6-foot bottom and a 1-on-4 side slopes. Guardrail was only necessary at the bridge abutments and was designed for the associated conflicts. 3 stages of MOT were needed. Stage 1 consists of temporary barricades to limit confusion due to the construction. Stage 2A connects the new eastbound lane to existing through the use of temporary signals. Stage 2B diverts traffic onto the proposed eastbound lane, and one-way traffic is maintained with the continued use of temporary signals. Stage 3 offsets traffic on the new roadway to allow the deconstruction of the existing bridge and pavement. Permanent signing and pavement markings follow the design of no passing zones within the project and reflect that with the associated materials used. Throughout this project, we would like to thank the following people: Michael Vogt, Chris Sikkema, and Dr. Haynes and Dr. K for their continued help. We would like to now open for any questions.
John Polasek, when you designed the grade, what you needed to know what the beams were and the underclearance for the high water level of the river. Was that taken into account? Is there something you used for the elevation that you could put in there for your structure?
Yeah, so one thing that we did analyze is the existing bridge is currently if off the top of my head, I believe it's 35 feet off of the river. And our actual proposed bridge, based on the vertical alignments, is actually higher off the river than the existing bridge. So due to that account, we didn't do any analysis on the river. During this process, we're only involved in deciding the location of the bridge and through the vertical alignment, the height of the bridge.
Is there any history of what the high water level was through that area?
No, this river actually isn't a very high flowing river. It's more or less a moving swamp, if you want to consider it that. There is water movement, but the flooding does not affect the bridge.
Okay.
This is Janine Cooper with MDOT. Couple of questions that I have for you. First, when you were considering the alignment on the south side, did you observe or anticipate any overlapping issues with the foundation between the two structures that might interfere with the constructability of that south side? And then the second question I have is, were there any archaeological impacts? Ontonagon has, well, the whole UP has a pretty significant Native American presence, and were there any archaeological issues there?
Yeah, to answer your first question, it was proposed by MDOT to use a 60-foot offset for the bridge. They found that this would not be in any conflict with the existing bridge. And to answer your second question, there was no information about any archaeological details within the bid package. So we moved forward assuming that information.
Okay, thank you.
This is Tim Mitchell. I have a couple of questions. I'm sorry if I missed something, but was there any consideration given to using the existing abutments as a cost savings measure?
Yeah, due to the fact that we have no detour routes available, we weren't allowed to use any of the existing bridge because of the new bridge had to be completely constructed before any traffic could be moved onto it. So there wasn't any shared materials between the bridges.
Okay, yeah, that makes sense. I probably missed that part. The second question I have is, did you consider the differences, or why you were getting the differences of a 3-inch asphalt thickness, which seems awfully light to me? I don't know what the truck traffic is, but it's a state route. And the 6 inches that you ultimately, or 6.5, or whatever it was that you ultimately came up with, it just seems like there must be something in the calculation to come up with 3 inches that maybe was not right.
So for our roadway, we only have 8% trucks, and our daily volume is 1,425-ish. So using AASHTO's design 1993 design guide, that's how we determined our minimum thickness of that 3 inches. But then after we went back and checked with MDOT's preferred thicknesses for application, and using our mixture types, we came up with that 6.5 inches that is necessary in the superior region.
Did you check that the 1.5 inches is the adequate thickness for the 5E3?
Yes. Yes.
That's the lowest. All right.
Mm-hmm.
Okay, thanks.
Any other questions out there?
Okay, this is June O. You had the MOT plan based on the current traffic volume. You don't have any concern in terms of maybe delay or any kind?
I'm sorry, can you repeat the last part of your question?
you had already MOT plan, so I didn't see the actual number of the traffic volume. Based on your traffic volume, so would it be enough to maintain all the traffic, or you are expecting some maybe significant delay?
Yeah, Kyle, I can answer this if you'd like.
Yeah, thank you.
With a average daily traffic volume of 1,400 cars, that roughly breaks down to a car a minute. This bridge section is only about half a mile of the total project. So due to that fact, we feel that there's no expected delays of incoming traffic from both directions with the use of the signals that will help mitigate the impact of the low traffic volume.
Right, thank you.
Any other questions out there?